Okay, so I would like to take this opportunity to thank Sergey and the organizers of this beautiful conference for giving me the opportunity to report to you our research in the past decade or so in this direction. And I gave the same talk actually 2 months ago at the European Dynamics Days in Aberdeen, Scotland. And I noticed that a couple of colleagues were also in this audience, so I apologize. You have to listen to this twice. But anyway, and this work was in collaboration with my previous postdoc, Professor Wenshu Wang from Beijing Normal University, and Professor Sasuke Boji from University of Aberdeen in Scotland, and then Professor Haifeng Zhang's group at Anhui University in China, and my current PhD student, Lingwei Kong. Now, our main problem is to get the data, and then from the data, you want to find the equations of the system and the structure of the system, provided that system is complex. So this is a general problem, and I'm going to begin with an experiment. And this was an experiment we did about 10 years ago to reconstruct a real social network. And so basically on one Saturday morning, we invited a group of students from Arizona State University, and actually 22 students, and to play a game. And among those 22 students, some of them are friends, and some of them do not know each other. So naturally, this is a social network. And as you can see, for instance, the node number 13 has like 6 neighbors, 6 friends, and some other nodes like number 8 only have 2 friends, and so on. And so this is a sparse social network. And so we're assuming the connecting structure of the network is unknown. And now, how can we infer the network structure using this experimental data? By saying experimental data, I mean the following. Each student, we ask them to play, ask him or her to play a game, and only with his or her friends. So in other words, if we look at node number 12, and he or she is going to play a game with node number 17 or node number 9. And so the data we're going to record is basically the payoffs and the strategies when they play with each other. And we're talking about some kind of evolutionary game. And as you noticed, 2 students actually did not finish the experiment. It's node number 3 and 10. So we asked them to play to play this game. And we distribute a table like this, basically which records the strategies each student used, and then the payoffs they get. And so those are the sample experimental record of the 2 players. And the payoff comes from this type of game. And so we just say, well, they're going to play the so-called PDG, the prisoner's dilemma game. And basically, if you happen to know this game, is both caught by police, and if both cooperate, and then they get relatively light sentences, and if both defects in telling liars, and then the punishment is very severe. But there are cases when one actually defects, another cooperates, then actually the one who tells a lie is going to go free. Okay, so this is a very standard PDG game, and we ask them to play. So by the payoff is calculated from a matrix. And basically we say, well, there are 2 strategies each player can use. One is so-called cooperation. And because there are 2 strategies, so it's very convenient to use binary representation. So this factor will be cooperation 1, 0, and the defection will be 0, 1. And the payoff matrix is given by this 2 by 2 matrix here, where B is the parameter. So we can calculate the payoff of agent X from playing PDG with agent Y in this fashion. Basically takes this vector inverse, the transpose, multiplied by the payoff matrix, and then multiply the strategy used by Y, and so on. So it's a very easy task that student can use. And then suppose we have a network of agents. They're playing games with each other. Of course, then we know we have adjacency matrix. While the element is 1, if they are friends to each other, is 0 if there's no no connection. And then the payoff, like I said, is given by this one, this formula. Now we are going to then, based on the payoffs in the strategy, those are the data, the actual data, and we're going to do a compressive sensing to get the full social network structure. And so the question is why we use compressive sensing. Now we can write down the payoff of agent X at time t in this way, and basically at the time t, it's going to play game with, we count, if he or she has multiple friends, and each round is counted time t. Okay, so each round of game, playing with each of his or her friends is counted as a one-time step. And then the payoff, it can be written as basically this combination of all those payoffs, the sum of all the payoffs. While the matrix element, if it's 0, of course, there's no payoff. It's no friend. And then now we are going to look at the time moments. So this is for a specific time t, but we're going to pick up a few time moments, saying t1, t2, until tm here, and we list all those payoffs as a vector here. And then this x vector, capital X vector, basically is a connection vector of agent X, which are the adjacency matrix from X to other nodes in the network. So that would be the vector we try to figure out. Now this quantity here, STPS, basically can be calculated from data. So we organize those data, all the data here at different time t. The first row corresponds to time t1, second to t2, and so on. And then we organize this into this matrix. Then you see all those equations, those linear equations, can be written as in a fashion like this. Well, y is something we know from data, and phi is also a matrix we know from data, and x is something we need to figure out. So then you see, well, to solve for x from this linear equation is easy, right? And you might just say it's easy, but the problem is this matrix is not square matrix. This matrix actually has a very long structure in the horizontal direction. In the vertical direction, it has a few rows, but it has lots of columns. So this is ill-defined from the conventional point of view, and there's no solution. Okay, and in general situations, that's if this vector here, if this vector has lots of non-zero elements, then there's no solution. Okay, but there is a caveat here. That's a catch if this vector is sparse. In the sense, if only a few of those elements are non-zero, most of those elements are 0. Under these circumstances, then this has a solution, and this to obtain a solution like this is called compressive sensing. And now we know a good thing about those regular, conventional complex networks. We know they are sparse in the sense that those adjacency matrix elements, if you focus on any individual node, most of those elements for a sparse network will be 0. Okay, so it satisfies this sparsity condition. And so that's a sparse optimization problem here. Now, we are going to then do something. We say, well, we solve this compressive sensing problem to get this coefficient vector. And we have to then we solve for another node, focusing on another node, we solve a coefficient vector. We have to make sure that these solutions are consistent with each other in the sense that if y is a neighbor of x, and then when you calculate the coefficient vector from x and from y, it must be that x is also a vector of y. So you have to check this consistency for all the nodes in the network to get the full network structure. So that's basically the idea. Now, let me just briefly mention compressive sensing is something that was invented in around year 2006, and it's has lots of broad applications in engineering, different engineering disciplines. And then basically the problem is like this: we have a measurement vector here. Then this is a very long, horizontally long matrix, and we have something we need to solve. And this something we need to solve has only a few spots which are not 0. Okay, so if the number of non-zero elements is k, if k is less than or equal to the number of elements in this measurement vector here, and if those k and m are much, much smaller than the horizontal dimension of this matrix, then this gentleman proved that there's a mathematical theorem. And basically, and saying you can get a unique solution for that sparse vector. And so some results, from our experiment is as follows. And we have just arbitrarily set some parameter in the PDG game. By the way, what kind of games really do not matter here. Okay, you can play a different kind of game, you will get the same result. And now these are the success rate of existing links and success rate of non-existing links. And as you can see, if the data amount, we normalize the data amount to 100%, and altogether in that experiment, we have 32 data points. Basically, each student played 32 rounds of game, and it was her friends. And so 1.0 means 32 data points. So as you can see, around 60% of around 20 data points, and those both success rate already reaches 100%. Okay, so that's for that specific. And then we also observe, if you check the normalized payoff with different nodes, and then we find some interesting phenomena where the winner who gets the most payoff actually turns out to be some node with some very small degree. And this is actually a well-known phenomenon in social science. Okay, so it's also reflected in our experiment. Now, let me briefly discuss then how do we find equations of dynamical system from data only. Okay, suppose we don't know the equation, but suppose we underline the dynamical system is given by this standard form. And so our goal is to determine fx, which is a vector, from measured time series xt. So we just do power series expansion of the component of this vector. Let's say the x component, j's component here, and the j's component of this velocity field, you just expand in terms of a bunch of power series up to order n, okay? And then xk is a kth component of x, and this is the highest order power is n. And then these are the coefficients to be estimated from time series. Now, if all these elements, most of those elements are non-zero, then I'm not doing anything useful. Basically, it's the same problem as before, okay? But the catch is if most of those coefficients are zero, and then you can do something about it. So in this case, we will have altogether, if we expand up to order n, then there will be 1 plus n raised to the power of m coefficients altogether. And m, of course, is a dimension of this vector x here. Now, if x, like I mentioned, if fx contains only a few power series terms, most of the coefficient will be zero. Then we have it's a good news for us. And those applies to regular chaotic systems like the Lorentz system, Rossler system, and so on. Okay, and a bunch of even includes a bunch of standard partial differential equation systems we know, we study quite often as the systems. All right, so now let me give you a concrete example. If I'm looking at the three-dimensional space like a Lorentz system, x, y, z, and if we expand to the third order, and then the total number of coefficients to be determined, it will be 64. And then the first component of the velocity field can be written in this fashion, and the coefficient vector basically is 64 by 1. And as a measurement vector, you organize this, expansion here, and it will be 1 by 64. So this fxt, the first component, can be written basically as a inner product between this vector and this vector here. So we continue looking at different time moments, just say 11 vector data points. And we use 11 because we need to figure out the derivative from data. Okay. So at the first moment is given by this, and the second moment, and so on. And we list until 10 time instance. And then we get 10 equations like this. And basically, then the derivative vectors is organized in this fashion. We need 2 points to estimate the derivative. So that's why it's data points is 11 data points. And the measurement vector is basically the G, as you can see now, it's a 10 by 64 matrix. So it has a structure like this. And then we have this equation. This equation is nothing but the compressive sensing formula. Okay, basically the setup of compressive sensing. And then we can move to a different vector, a different component of the velocity field. All that needs to be changed actually is just this measurement vector here. Okay, actually the projection matrix, this matrix remains the same. So you can do this for the second component and third and so on. And now we can also do this for oscillatory network here. And if we have a complex oscillatory network, which Cij basically is a coupling matrix here, and so the ith node is written in terms of a differential equation like this, and the Cij is a coupling between j and I. So actually, because xi and xj are m-dimensional vectors, so this Cij actually is a local coupling matrix. In this, it's m by m coupling matrix. So as long as at least one coefficient, one element in this matrix is non-zero, then nodes I and j are coupled. So we're assuming that fi, basically this can also be expanded into a few power series terms. And then basically we can organize all those vectors and into a column vector like this. So this column vector is very long. It's actually n times m times 1. So it's a very, vertically very tall vector here. And then the network equation basically can be written as in this way here. And then this gxi, of course, is given by this. So we're basically going back to the previous setup, except that our dimension here is, in terms of bookkeeping, it's more sophisticated, but the basic principle is exactly the same as before. And we are talking about basically dx dt. Before we talk about fx, now we have some kind of more sophisticated form. And so it's a very high dimensional dynamical system. And if we talk about complex networks, for example, random small with scale free, and the node-to-node connections are typically sparse. So it naturally satisfies the sparsity condition. And then in power series of expansion, most coefficients will be 0. So this guarantees the sparsity condition for compressive sensing. And so compressive sensing can be applied in this case here. Okay. So now let me then discuss some limitation of this problem. And by the way, there are 2 review articles we wrote, and one in 2016 and in Physics Reports. Another one I wrote, and it's a tutorial and published in about a year ago in Chaos. And I'm going to explain why I wrote this paper a little later towards the end of the talk. And now I'm going to give you one example where the method I just described fails completely, okay, totally completely. And this is this simple model here, as you probably know from Chaos nonlinear dynamics. It's Ikeda map. It's a 2-dimensional map which describes the dynamics of a laser pulse propagating in an optical cavity. And now, if you look at this structure here, x, y are basically the dynamical variables. And then we have a phi here. Phi is a phase. So this phase depends on the dynamical variable in such a way. Now, imagine when you want to expand this form, this kind of function, into a power series of x and y. Every single term will be there. So this is a dense, basically, coefficient matrix. And so therefore, sparse optimization is not applicable for finding the system equations. So then you say, well, what do you do in this case? In this case, our solution is more recent. Actually, use machine learning, okay? Machine learning, and then you don't have to worry about the exact equation of the system, but instead you build up some kind of twin, digital twin of the original system. And by, AI, in basically machine learning. And so I'm not going to discuss the details of build up those, digital twins and machine learning. Just to show you some results, this is for the Ikeda map. The ground truth is here. This is attracted slightly before a crisis transition. And at a certain point, there will be a crisis transition where this attractor collides with the basin boundary and it is destroyed. And then after that, this chaotic attractor becomes a chaotic transient. And then the system basically diverges to another attractor. And so this is what happens to the ground, the real system here. And now this is what predicted from our machine learning. Basically, then before the crisis, it predicts exactly, statistically identical chaotic attractor as before, and before the crisis. After the crisis, it's going to predict, yeah, you're going to have some trouble. This trajectory is going to escape, but where it can escape to cannot be predicted because we train the machine only in the region of chaos at a number of different parameters, actually 3 different parameters. And so we never give the information of this afterward, even after the critical transition to the machine. So therefore, it will not be able to predict correctly the trajectory afterwards. It can only predict, yes, the systems are going to collapse, but where it collapses to cannot be predicted. Now, this is basically, we did this with a reason, because if you want to predict the system collapse, and if the system has already collapsed, you probably don't have to do anything, right? So we assume the information after system collapse is not available. Okay, so that's why we did the training only using the information available, which is before the collapse. And now here's a prediction of the so-called transient lifetime, because we say, well, after the crisis, you're going to have some kind of transient chaos. Then you ask, on average, and if you take an initial condition, it's going to do, move chaotically for a while before it escapes. But the length of the states behaves chaotically is the length of the transient lifetime. Now, for different initial condition, this lifetime will be a random number, but it has a distribution. So what I show here is basically the distribution of the transient lifetime, on a semi-logarithmic scale. And you see 2 traces. One actually, 2 arrays of data points. One color is from the ground truth, from the original system. Another is predicted by the machine. So you don't see much difference between the 2 cases. So that's what we need to do. But in a sense, it's not finding the system equations anymore. It's just that you build up a very general machine learning, model. And it's like a twin of your original system, digital twin of your original chaotic system. Once I have built up this digital twin, I can do all kinds of simulations, computational study of the digital twin, and to predict if the system is going to collapse or have some dangerous behavior in the future. And of course, you in reality, when your new measurements available, you probably take into those new measurements into account to refine your digital twin. So in this way, in real time, you can always keep up your digital twin model to make sure that you can have reliable prediction, of the system behavior. Now I'm going to switch gear a little bit to talk about networks with high order interaction. This is more recent work we did, and basically, Professor Strug has already talked about, this, mentioned this very briefly, but let me say, well, this is this one node was by itself, it's called 0 simplex. If we are talking about a regular link, it's called 1 simplex. But if we talk about 3-body interaction, and this is called a 2 simplex, and so on. And so 3-body interactions actually are different from 2-body interaction in the sense that, well, if you think about, a regular, a conventional social network, if 2 friends get together, they figure out something, then you imagine 3 friends get together. They figure out something. Those something will be different, okay? And probably more evil, idea, okay? So once you have many body interaction involved in the network here, then actually the interaction structure, the network structure is different. So that is why, we represent a model, very simple model here. As you can see, those are regular links, but the 3-body interactions are represented by those yellow triangles. And if you want, say, well, mathematically, how do we distinguish them? Mathematically, then this is what, the Kuromoto model Professor Struggles wrote down. And basically, the, phase coupling here, this is a regular term. Those links, just the links that he was talking about. But the 3-body interactions needs to be described by this tensor of order 2, of rank 2. tensor, and then with this kind of interaction, and the full body interaction, and so on and so forth. So they are kind of different. And in real world networks, and this kind of patterns actually occur quite often. So I have 4 examples here, from those different systems, from different data and the real world system. And basically, this is, I took from this paper published last year. Okay. Now, our problem is we try to reconstruct complex networks with high order interaction. So suppose we have a network structure like this, where these line segments are just the regular links. Those triangles, something you would like to predict. Those are the high order interactions. And now, to make life a little simpler, I'm going to assume that we're going to have binary data. So in a sense, binary type of dynamics, and maybe disease propagation. So each node, either you are infected or you are not infected. So 2 states and so on. So the first step is to build up so-called data matrix, while the horizontal direction here denotes basically different nodes, like node 1, 2, 3, and so on. The vertical axis records the data of the node you measured at time t, t plus 1, t plus 2. So it's a matrix like this, as you can see. Now, the very first thing to estimate is, let me first focus on those links, just those regular links. And then we're going to estimate this conditional probability. Or if it's a node j and I, we'll say, well, at time t, node i's state is 0, node j's state is 1. Under this condition, what is the probability that node I at the next time step will be 1? So basically, you can count this probability from this column here and this column to identify if it's 713, then you see 713, this is 13, we are going to have 1 here. And then 7, basically, we're going to see, well, if 13 is 0 and 7 is 1, what is the probability for 13 to be 1 at the next time step? You count this and you actually find that there's 1 case out of 2. So this probably is 1/2. Okay. And now with this, then you basically count, all those probabilities, and you bookkeep them and keep them there. And then there's 1 simplex, basically J to I is an event that the node J has a direct impact on the state of node I. So our goal is to find this probability, the probability that node J has a direct impact, on node I. Basically, it's denoted as the probability, the conditional probability that it has some influence, and under the condition at time t, state of node I is 0, state of J is 1, but at time t plus 1, state of node I is 1. So we need to figure out this probability, conditional probability. If this probability is positive, in a sense, you can distinguish from 0. So that indicates node J is a neighbor of node I, but this is not easy to be found, okay? And this takes a bunch of mathematical machinery actually to go from this kind of simple counting, to this probability, which I'm going to describe in the next slide. But for now, let me see, well, what if we want to figure out those triangles? And you basically then construct the same type of data conditional probability. In this case, we're going to take 3 nodes, I, J, K. And the conditional probability is at time t, node state of I is 0, but at state of J and K are 1. So this is 1. And then at time t plus 1, the state of node I is 1. So we figure out this conditional probability. This is very easy. You just read from this data matrix. And for the cases I show here, this is just 1 here. And then we follow the same suit. We say, well, we're going to figure out 2 simplex. JK goes to I. This is event, and that is synergistic effect of node J and K has a direct impact on state of node I. So basically try to find this conditional probability. And if we can determine that this is different from 0, so that indicates the 3 nodes actually forms a 2 simplex. But this is not easy as well. Okay, so the point here is these problems, this simple problem and a relatively more complex problem can be solved actually by so-called the likelihood method. So first you construct a likelihood function, then we're going to maximize the likelihood function use the so-called EM method. It's the expectation maximization to figure out those links, those probability. Then we, of course, going to remove conflicts. And then we're going to remove conflicts and then impose threshold condition on these different probabilities we figured out. So here's one example. If we are looking at just one simplex, we have a number like this, bunch of numbers like this for node number j to node 13. J here comes from 5, 7, and so on. And then now this is from jk to node number 13. Jk can be from those kind of combination. And now with this is a data structure we get. And with one simplex, as you can see, it's very easy to be distinguished, whereas the red dots indicate there's no connection. The blue dot indicates there is a connection, while the vertical axis is this probability, Pj goes to I, and the horizontal axis here is a node index, just 1, 2, 3, 4, until whatever the number of nodes you have in the network. So in the first case, you see this is a clear cut. We can set up a threshold here to distinguish links with non-existent links. So this is great. But the problem is here. When you try to figure out the triangles, and you see these blue points tend to be higher, and then those red points tend to have a spread. So it's very difficult to place a threshold in that. Okay, so that's a problem. And actually, if you place some threshold which you think is the best threshold, you still get a network structure like this with those errors. Those two gray triangles are basically none there. So those are just a complete mistake or errors. And then we figure out the so-called two-step method. And then basically, we know the particularity of the simplicial complexes stipulates that, if we look at the two simplex, then the other two nodes forming, a two simplex with node I must be neighbors of this node. So therefore, it is not necessary to calculate this probability if node j or node k is not a neighbor of node I. So that simplifies things a lot, because if they are not neighbor, obviously they will not belong to this triangle, okay, two simplex. And so this way we get a reduced data matrix, then we repeat the whole thing again, and then you get this, and then this way is little bit better than the previous case, as you can see here. But we still have ambiguity. Then this ambiguity can be resolved actually by doing the consistent check. Basically, you say, well, if j and k are my neighbors forming a triangle, then I and j must be also a neighbor of k forming another the same triangle. And so you check 3 nodes individually, 3 triangles to make sure they're consistent. After you do this consistency check, and you eliminate certain things, and basically then this situation can be improved, and it turns out we can actually correctly predict the final the correct matrix and network structure here. Okay, so let me see on the time and what's okay, good, yeah, good. So then more recently, we did some machine learning, basically prediction of network dynamics with privacy protection. The traditional way of doing network structure prediction, you use data to figure out the network structure. And it's basically, you assume there's no privacy involved. And every node collects everything, and every agent collects everything from the network, and the network, is there. And so there's no privacy protection. But assuming, suppose you will have a scenario like this. So as you can see, this is a simple network structure here. And those are the timestamp, 3 bars, colored bars indicate actually the timestamps of the data you collect. So 3 bars means you have everything, all the time series data from everything. But suppose you only have partial timestamps, and like this, this client 1, agent 1 collects only the time series at a certain point, and even though the network structure has no idea of the network structure, so incomplete knowledge of network structure. Client number 2 collects some data at a different time, and from his or her point of view, the network looks very different. Okay, so those are the, and then basically they don't know each, they don't share data with each other. They don't share the collected data from each other. So this is a privacy protection, right? And now we can imagine another scenario where the time series are complete, but only from partial nodes. In a sense, one agent can collect time series from T1, T2, T3 from certain collection of nodes. Another agent collects, time series, complete time series, but from different set of nodes, and so on. So they still do not share everything. So there's still, lack of basically complete knowledge of network structure. And so there's a privacy issue involved here. So the question is, once you collect data in this fashion, you try to protect the privacy of those clients, agents. How do you figure out the network dynamics? Okay. And so we developed the so-called federated graph neural network. And basically saying agent number 1 collects data, partial data, and agents, and a different agent collects different set of data under those scenarios. And then they basically deliver everything to a central network, so-called global model. And this is a federated FGNN neural network model. And it's a pretty standard model, in computer science. But you input all those, and then this global model is going to integrate, synthesis all those data, and then run network simulation, and then basically figure out the network dynamics. Okay, so I don't have time to go through the details here, but this is a paper that is going to be published in very soon. And now let me come back to our original question of finding the system equations. And I should actually give a brief history of this area of research. The very first paper in this field in nonlinear dynamics is equations of motion from a data series. It's actually by Crutchfield and his collaborator once he was still at the UC Berkeley. So that's a very early paper on this topic. And they actually used basically time delay embedding type of technique and employing some kind of information measure. And the problem with this early method is it has a very large error. Even for a very simple system like a logistic map or Hinton map, it creates large error. Okay, you cannot predict precisely what's going on. So this is our work, and we developed this compressive sensing technique back in 2011. And then basically it's a this need to find it. Although if you look at the title, it's a very bad title, by the way, okay, because it did not say we find the system equations from data. And at that point, I thought while predicting catastrophes or critical transitions in nonlinear dynamical system is very important. And I failed to recognize actually a simpler term saying like finding equations could be a much more popular cell. And so it's a bad title, but actually the need to find the system equation from data is clearly stated 3 times in our work. And so this is one time, okay? There's another time here, and this is another time, okay? So we basically say you need to find the system equations first from data using compressive sensing. Then you do the computational simulation of those, the system equations to figure out if you have a crisis, critical transition. So we did this. And now 5 years later, and I should also say Professor Eric Bolt from Clarkson also conceived the same idea of basically our idea at approximately the same time. But he thought this idea was too trivial, so he did not even bother to write a paper, okay? His standard is very high, by the way. Okay, but anyway, 5 years later, exactly the same idea was published by the University of Washington group. And look at that title here, Discovering Governing Equations from Data. It's a very simple title and a very intuitive title. So that's why, this paper has lots of citations. But anyway, so the reason that I wrote this review article, tutorial article for Chaos, which was published about a year ago, is basically try to set the history correct. And this paper was 5 years later than our paper, and exactly the same idea, but half year before they published their work, I actually gave our work to Professor Kurz. And at an Air Force, program review meeting, and Professor Kurz was talking about finding the equations of Lorentz system using data. I stood up saying, come on, we solved this problem 5 years ago. So I gave him all the material, all the papers we had. But nonetheless, the paper is still published in Peanuts. And so I said this, and I know that I might upset you somehow. You might think me as a grumpy old man, with angry voice here. But I think as scientists like you and me, it is our secret duty actually to make the history right. Okay, and so with that, let me conclude to say that sparse optimization can be exploited to find equations of nonlinear systems and the structures of complex networks from data. This method would fail if the sparsity condition is not satisfied, like Ikeda map. And so this is still some kind of unsolved problem. If you really emphasize, you really want to find the equations, I don't think that's a way to do that. But the alternative solution is to use machine learning. Oh, by the way, I should say that machine learning can be exploited for this similar type of machine learning for model-free database prediction of a variety of phenomena in nonlinear complex dynamical systems, such as crisis, transient chaos, amplitude deaths, onset of explosive synchronization, and even tipping points, and all from my group, we're writing those papers actually. And then high-order structures of complex networks can be uncovered from data through statistical inference. And the network dynamics can be predicted without compromising privacy. So with that, I thank you so much for your attention.
Thank you, Cheng, for this fantastic lecture. We still have time for questions. Yes, Axel, please.
Hello, I'm Axel Timmermann,
Yes.
Director of the IBS Center for Climate Physics.
Yeah.
And I remember Jürgen Kurz and Henning Voss, they used alternating conditional expectation algorithms in the early 2000s to derive equations from data. And we applied these methods in 2002 to climate data in order to derive nonlinear dynamical systems. We called it empirical dynamical modeling.
Okay.
So when you talk about setting the history straight,
Yes.
maybe that's something also to look into. It has been
Yes.
applied in the climate literature actually extensively. And
Yes,
maybe
yes.
you would like to have a look at that.
Yeah.
And in
yeah.
particular, Jürgen Kurz and Henning Voss paper on these methods, they are quite spectacular.
I apologize. Okay. Yeah, I just look at the things, I come into my mind and it's limit time. But thank you so much. Next time I will include Jürgen's work, early work in this direction. Yes. So actually it's a very extensive list also using neural networks and so on in early years. Yeah. Definitely I'm not being comprehensive. My apology. Yeah.
Okay, other questions? Yes, please, here in the front. Wait for the mic.
Thank you for your nice talk. When you construct this network from data,
Yeah.
Can you recognize or guarantee if the network is unique one? I mean, otherwise, are you saying that the network you have found is one of other possible networks?
Oh, okay. Yeah. And the question is whether or not you find the network from data, whether or not it's unique.
Yeah.
You can have different possibilities.
Yeah. Can you guarantee or identify that?
And this, if the sparsity condition is satisfied, this is guaranteed. It's mathematically guaranteed. It's a unique solution. Yes.
Okay, thank you.
Okay, there's a question just in the next row, please.
No, it's not on. It's not on.
Oh, yeah, I remember that the PNS paper wrote a linear combination of analytic terms and did sparse optimization.
Yes.
Did you do exactly the same method?
Exactly the same, because those are so-called library terms. Those are the power series terms.
Oh, okay, thank you.
Exactly the same power series terms I was talking about.
Oh.
Yes.
Okay, I think the last question is in the front. David, please.
Thank you. So I have a comment and a question. So the comment is that I assume that the prisoner dilemma game that you used was mixed strategies, because otherwise there is a unique rational solution and there is no, it's not a stochastic time series. The other thing that I wanted to mention is compressed sensing has its own problems in terms of noise, in terms of the number of examples that you need in order to get solutions under the L1 constraint or whatever constraint you are putting.
Yes.
So how sensitive is your method to noise, to measurement noise?
Compressive sensing is sensitive to noise. If noise is a little bit, I mean, let's say more than 5%, and it's not going to work correctly.
And in terms of the number of equations or measurements needed, because under L0, it is exactly the same number of connections, but usually people use a measure that is L1 or L2 or whatever, and it requires many more measurements.
That's right. Yeah, and actually after, in the past 10 years or so, there are different variants, different improvements of this compressive sensing method to include different combinations of optimization, different orders of optimization that can solve actually, the noise problem to some extent. But obviously I did not have time to include all these works. Yes. Thank you for your comments. Yeah.
Okay, to give our Zoomers a chance, there is actually a question, or there are two questions in the, if you just turn around, Ying Cheng, you can see it. Yeah. Could describing a system in terms of its spectral dimension also help to characterize its localization? Question one. But that's probably from the previous talk. Okay, here's yours. Is sparsity the only thing needed for compressive sensing?
Yeah, so for the first question, describing a system in terms of its spectral dimension also help to characterize its localization.
I think this is an old question which refers to the previous talk. Let's unfortunately ignore this for the moment.
Because I did not recall talking about localization.
No.
But anyway,
the next one. The
sparsity is the only thing needed for compressive sensing, and at this point, yes.
Okay.
Answer is yes. Yeah.
Thank you.
Other diameter between its centroidity, other features, the characteristic of network actually turns out, do not matter so much. Sparsity is the only requirement at this point. Yes.
Okay, I think we should stop here, and let's thank all the speakers of this morning session.
Okay,
thank you very much.